Oh no, it's on the solar side.
Exactly. So, as those of you who talked to me already know that the talk with that title has already been given. I had a call and talked about this yesterday. So, if you look at the actual abstracts of the talks, you'll find that there the title of the talk is correct. So this is the work that has been supported by ICAM and was done in collaboration with the group at Karlsruhe. So ICAM generously allowed me to travel to Karlsruhe to work with Jörg Schmalian, his former diploma student Paul Bayreuther, who is now applied in his PhD with Yuli Nazarov and Peter Kort. So the advantage of that is that, first of all, I get here to give a talk about something I don't know, because if you look at the title, I'm not an expert in semiconductors, I'm not an expert in quantum optics, I know a little bit about superconductivity, but 1 out of 3 is not so bad. And the other thing is that, of course, the advantage of working with these people, that you talk to Peter and Paul and you say, well, you know, do you know how to do this? And within 2 hours they tell you, yes, here. So a large fraction of calculation has been done by them, and here is the actual answer. Now, before I came here, I actually asked, I wanted to put some image here that would emphasize that, you know, annual conference of ICAM is something that we're celebrating here. And so I asked my friends whether they can find an appropriate image, not a cartoon, I can't compete with Craig on that. And Rivaz Ramazashvili, who some of you know, sent me this picture, which immediately made it into my talk. So this is something that happens in Toulouse, apparently every year.
That's so cool.
So festival I came and it says be extreme. Which of course the advice we all should take to heart, especially when writing our proposals for the next round. Now, let me go back to...
so what does ICAM stand for here?
Institut Catholique des Arts et Métiers. So Catholic Institute of Arts and Craft, specialty. So it's an educational institution in Toulouse, which apparently has been started by Jesuits at the request of local manufacturers a long time ago. Emphasizes engineering, business, and things like that. But once a year they have this festival, which, as far as I could tell from the website, is mostly electronic music. And that's the poster for it. So
We're definitely behind in the public relations business.
absolutely, we need to make a poster like that. We need to decide whose faces go there.
Masks too.
All right, so now let me talk about what actually motivated us to do this originally. And that was the fact that there are light emitting, so for introduction, there are light emitting diodes. And for me as a non-expert light emitting diode, I had a p-n junction. And of course, what happens generally speaking is that there are more electrons on one side, more holes on the other side, and there is a depletion layer in between. And then you apply to this thing the forward bias, and therefore you allow electrons and holes migrate into the depletion region, and they recombine, and they emit photons, roughly speaking, at the energy equal to the energy of that gap. So what we asked ourselves is what happens if I now proximity induce superconductivity in the leads. So imagine I have a p-n junction with superconducting leads. And you can imagine that because I now have Cooper pairs, I can produce pairs of photons. And the question that was relevant there is the question that we know is important for quantum optics is, can I transfer the coherence of the superconducting state to photons somehow? So that would be a theoretical motivation. In fact, there would be no motivation if there wasn't an experiment. There are actually a series of experiments by Suemoon et al. This is the actual structure they use. So there are niobium electrodes on top and bottom on top here. And therefore, this is not quite the system we're talking about because superconductivity is induced only on the n side. And then there are two sort of different layers here, but that's mostly to enable the tunneling of the Cooper pairs on the forward bias into the depletion region from the niobium electrons. And then there are normal holes coming from the other side. And if you try to operate this device, first you try to operate it somewhere where niobium electrons are non-superconducting, and you see that essentially what happens is there is emission and the energy which corresponds to the energy of this gap. So this is my equation. Of course, the intensity here depends on the current you drive through the system. So the current here is 1 milliampere. And of course, if you reduce the current, you'll see almost nothing. And that remains almost true once you go below the superconducting transition of ion niobium electrons. And here are the results. So this is the current that is 1/4 of what it was used to be. And you see that above the transition temperature, you basically see nothing. But if you look at the intensity of the luminescence, you see that it's growing as you go below the transition temperature. And in fact, it grows as the superconducting current grows. So this is not a crazy question to ask. What effect superconductivity might have? Yes?
What is the degeneracy temperature of the leads, and is the temperature below or above it?
The degeneracy temperature for the, oh, you mean the, if you just estimate it, yeah, estimate the density.
Which you don't know.
It's nowhere near. I mean, this is 10 Kelvin, right? This is,
Well above or well below?
no, so basically these are actually, if you look at this picture, you can
What's
answer
the
the
doping
question.
level?
So the Fermi energy is basically already in the band here. So this is actually fairly high density. So it's fairly high effective Fermi temperature.
So I can think of it as a
So-
degenerate electron hole gas.
So it's actually electron gas, yes.
It's hard not to make any comparison.
Oh, so it's a classical gas.
No, it's not.
It's a degenerate gas.
It's a general, yeah.
I'm trying to get
Yeah, so the Fermi temperature is very high compared
very high
to
to
GC.
see.
And that's what you can see basically here. So anyway, that was the motivation. So now from this it follows that superconductivity at least does something to luminescence. And now we can ask the question of, we can set up a problem. So I asked already whether photons carry some coherence of electron state. And generally this, as I learned in the process of working on this, it's a question of whether you can use solid state devices to actually to have non-classical photon generation. And apparently there are some examples where this can be done, and I know of two. One is by excitons and quantum dots, and the other is the 2-photon emission from the nonlinear optics crystal, and they give fairly low yield, and in the first case they still give sort of the Poisson distribution. So that's the motivation. Now let's set up the problem of the theory, so I need to write a Hamiltonian. So here is the model. And the model consists basically of the two leads. So here, the alpha stands for the conduction or valence band. So there is a dispersion, there is an induced superconductivity, and there is a photon field somewhere in my field, and there is a coupling, which tells me that if I kill a conduction electron, I create a valence electron, there will be a photon emitted in the process. Now, what makes this a little bit more complicated problem is that this is a non-equilibrium problem. Namely, because I'm using the junction under bias, the actual chemical potential is different in the conduction band and the valence band. In fact, the difference between the two is precisely the bias we apply to the junction.
Can you
Yes?
say what's V?
So V or C are the conduction of valence band electrons
In the quantum equation, electron
in any equation.
electron photon.
So I move electron from the conduction band to the valence band, and I emit a photon in the process.
So the superconducting pairs are always an ideal valence band or
Yes.
right? There's no mechanism for there to be a pairing between a conduction band and
No, because this is basically electron volt difference in energy for the TC, which is 10 Kelvin.
So it has to depend with it depends on the band gap of the superconductor.
Right, so the band gap is large
So
enough
this
so
is
that
large band
you
gap.
prohibit interband pairing. Yes. So, all right, so with that, now one needs to decide how to treat this problem, and the first inclination for a first inkling that something interesting is happening is not if you just write equations of motion for the photon operators and decide that, so you write an effective Hamiltonian for photons that to second order in coupling reproduces exactly the same equations of motion. Because it's a non-equilibrium system, there aren't all that many choices that we can use. So now this is the answer, and it has basically a couple of terms. So this is my original term. Notice that the frequency changed from something I call omega 0 to something called omega, which means that there is a correction to the frequency due to this. And then there is a single photon emission, and there is a double photon emission. Essentially, this is the term that arises due to superconductivity, and this is the term that in principle is responsible for the conventional luminescence. There is, however, again a caveat. Because this is a non-equilibrium problem, when I evaluate this coefficient, what I need to do, I need to integrate some fermionic equations of motion from some time long in the past when things were in equilibrium. So these actually contain fermionic operators, and because of that, they can't be treated as usual C numbers. For example, the coefficient and its own permission conjugate don't commute. So what one can do is to say, well, you know, I'm going to look at it as sort of the terms in Langevin equation, where if to second order, all I need is to evaluate the correlators of these things, and I know how to do it in any thermodynamic situation, and these will be not equal to 0. And in that case, we sort of look at this, and we can look at the old literature on quantum optics and know the answer. The answer is this is called quantum parametric amplifier, and this thing generates squeezed two-photon states. So now I need to explain what exactly I mean by this. So what are the squeezed states? Now imagine that I have a photon field, so I have an electric field. I can quantize it, so it has annihilation and creation operators. And I can introduce what essentially in case of oscillator would be the position and momentum operator, and here it would be more or less amplitude and the phase operators. And they don't commute with each other. And because they don't commute with each other, this means that if I try to look at the uncertainty measuring one and the other, there will be a Heisenberg principle, which in this case will tell me that the product of uncertainties has to be greater than 1/4. So generally speaking, the two you would expect to be of the same order, but squeeze state is the one where I reduce one of them below this threshold at the expense of the other. And it's called the ideal squeeze state if the actual minimum uncertainty is satisfied. So these states are important for quantum optics, and what they look like is the following. So imagine that I start with a coherent state that such is produced by a laser. So if I look at this uncertainty thing in my coordinates x1 and x2, this is a circle, which means that, roughly speaking, uncertainty in phase and uncertainty in amplitude is the same. You can create the state with reduced amplitude fluctuations, where you know the amplitude fairly well, but at the expense of knowing less about the phase. This will be squeezed state in this direction. And you can also define the phase a little better, knowing where minima and maxima are, but at the expense of uncertainty in the amplitude. So these are called the squeezed states, where I increase the uncertainty in one by reducing the uncertainty in the other. And essential uncertainty principle tells me that the area of this ellipse has to be at least equal to 1/4 in these cases. So it's also known that if I look at the parametric amplifier, it will generate squeezed states. And the squeezing will be not quite in the same coordinates, not in the same amplitude and phase as I described to you, but in some objects that will be rotated with respect to this by the angle that is related to the phase of this coefficient. And the amplitude of this coefficient will tell me how elongated this ellipse is. So these are the results that have been known in quantum optics for a while. And if I had simply the C numbers for my Hamiltonian, I would say, well, this is the Hamiltonian that actually produces the squeezed states, because I look at it and I say, well, first of all, this is a single photon generation. It sort of reflects non-equilibrium, gives me the usual luminescence. It does contribute to two-photon coherence, but the thing that actually gives me the squeezing ellipse is the second term, and this term has a phase, which tells me what the squeezing is, and it has some magnitude here. It depends on the coupling. However, and here I need to give a slight warning that if you look at the second term, you see that these are two operators that generate photons not in the same state. In fact, one is in the state with momentum plus q, and the other is state with momentum minus q. So I need to define to you what the equivalent...
what happens to the polarization? Are they opposite polarizations too?
Here. So in this case, there's supposed to be lambda there, and it was polarization. So this is all written for linearly polarized light. In principle, if I look for the system without inversion symmetry, I would need to worry about circular polarization, but I think it can be included in the same way. And at this point, they are the same polarization. So these are the same polarization. So this is just generalization of these operators I told you about for two different photons. And if you look at this quadrature, so plus and minus play the role of x1 and x2 in what I did before, you find that there is this anomalous photon correlator that tells me how squeezed or how elongated this ellipse is. So my task in some sense is to evaluate this object, and then I'll be able to tell you what the degree of squeezing is. Now, to do this, we actually used the Keldysh formalism. So we wrote the effective action using essentially the Nambu version of the photon propagators, and evaluated the propagator to the second order coupling. In addition to the electron, we introduced essentially a bath, which tells you that the photons decay out of the system. That gives me some equilibrium distribution at long times. So if I look at it first of all at some zero temperature, so here is the answer. And so you'll see two things at this point, that there is something here, and there is a phase that depends on the difference in phase between this superconducting photoparameters in conduction and the valence band. So which tells you, if you remember what I said, that actually the direction of this ellipse, what exactly am I squeezing, the amplitude of the phase, depends on the phase difference between the two superconducting leads, and therefore can be manipulated. In addition to this, I would like to know the degree of this squeezing, so I need to look at the amplitude of this thing. And if you look at this, you will find that there are, essentially look at the denominator, and you'll find that there are several, actually, use mine instead of this. So there are two peaks in this expression that are determined by where my denominator goes to 0. The first part, if you look at this, is just when the frequency of the photon is equal to the frequency to the bias of my junction, and that simply corresponds to the Cooper pairs moving from the conduction band to the valence band, emitting two photons. In this picture, which shows the anomalous propagator, this is this big central peak. However, there is a second peak here, which corresponds to what happens when the photon energy is shifted from that by the gap in the conduction and valence band. And the process that describes it is actually very simple. What I've done is now I broke the Cooper pair, and then I decided to allow it to migrate. So this process gives me a peak at the lower frequency, which is shifted by the sum of the gaps in the conduction and valence band. Now, of course, you look at this and you say, wait, there is a third process where I do the same thing, but only I do it from the valence to conduction band. The only difference in this is, of course, what happens is I need to spend energy to do this, so it doesn't happen at t equals 0. It has to happen at finite temperature. And so on the next slide, you'll see that we do the calculation.
Ilya, can I stop you and go
Yes.
back a slide to this perturbation diagrams? The one before.
The one before,
Yeah. I should have stopped.
there are a lot of circles here.
Okay, this one.
Yes.
So it's to second order, right?
Yes.
Is there a justification for doing it up to second order, or?
Well, I mean, electron-photon coupling is relatively small compared to other parameters. I mean, so at this point, I don't expect any resonance to occur, right? Which would be when I need to resum the whole thing. So I don't see it at this level. It is possible that at some point I'll start forming some, polariton type things.
For example.
But at this point, I don't see any evidence for this, so I don't see anything divergent. And I think this is partly because we allow the photons to escape the system, so there is a bath. I think if you put it sort of in a cavity where all the photons stay, you will probably get some resonant state. We just didn't get that. So, you'll have to suffer through the circles again. And then essentially, what happens is if you do the calculation at the finite temperature, you'll see that there are 3 peaks. And these 3 peaks correspond precisely to the just moving of the Cooper pairs, or saving energy by moving the body-liquid quasi-particles, which are in the sort of band here, to the valence band, as well as the activated part that corresponds to moving the electron, moving the particles from the valence band to the conduction band. Now, in contrast to sort of single mode squeezing, what happens is you can actually find that the same type of peaks are present in the density-density correlation. And I don't show the picture because they show sort of the same 3D structure. And since I was told that I should obey Frauenfelder rules, I am coming to my conclusions, where what I've done, what we considered is a p-n junction with proximity to superconductivity in the leads. What I try to convince you is that this thing can generate the entangled photon pairs. That the reason for that is that we can transfer the superconducting coherence to the photon production. In fact, the states are squeezed, and the degree of squeezing is controlled both by the phase difference between the superconducting leads and sort of depends on the tuning on the gaps as well as the so the peaks depend on the gaps as well as the central peak would depend only on the band gap. So with that, I thank you for taking questions.
Thank you very much, Ilya. Do we have questions for Ilya? Dan?
Just curious, I mean, so is there some proximity effect leakage then of pairs into the semiconductor?
Yes, that's the assumption. And so in
Well,
that,
that's an old measure, that's supposed to be 80s. That's an old measure.
yeah, but there have been measurements like this. In fact, there
A lot
are
of them.
measurements where you can
I've done quite a few
control the
myself.
critical current by the gate voltage in such system without luminescence. And so we know that this is
So
actually
you definitely can pull that off?
yes.
Yes.
Okay.
It's a long-range proximity effect, and especially in indium arsenide. It's like forever.
This
Here.
is probably science fiction, but is there any capability to link Joe's two systems optically, to Joe's and couple two superconductors optically using this?
So this is the next step, which we haven't done. You're asking now, well, if you imagine that I
Send these down by the optic
Get
and
some-
connect them up with the-
well, essentially get some equilibrium steady state for the photons
Yes.
and try to compute the change in Josephson coupling because of this.
Absolutely.
And the answer is there should be, haven't calculated because I think it will be g to the fourth.
But could I also use Peter Littlewood's favorite thing, example, could I synchronize two superconductors by doing this? Yeah, could I get two slightly out of phase things and send photons across and use them to...
That I'm not
Well, you
sure.
can have photon-induced tunneling, right?
Yes.
And so that, you have to worry about that being, there was a lot of work in the old days, was it a Josephson effect of photon-induced tunneling? And you can actually couple Josephson junctions. People do that all the time. So I'm sure it's been done. I'm sure they've optically coupled Josephson junctions.
That would be the one photon phenomenon.
Yeah, but the question is whether you can do the phase transfer.
So you transfer two photons and it's
Because-
like transferring a Cooper pair from one to the other. Or
So I think it's the fourth order process. So
G squared. Oh,
Yeah.
yeah.
so one needs to do more.
But even if it's weak, in principle, you
In principle,
could use it to synchronize your Cooper pair metronomes, whether they are right.
yeah. So I mean,
All together.
Peter worked now without my participation. I did some calculations to order g to the fourth just to explain the luminescence itself. Because at this point we focused on squeezing. I actually didn't tell you about what I started with, namely the signal, luminescent signal, or rather the radiating recombination rate. There he finds some relatively weak signal, but he tells me, and again, this is something that I have not participated in, that there are some vertex corrections that he's worried about. So
Can I ask one question?
that's possible.
When you go back to where all those circles were, and you have the Cooper pairs going from one material to another, why could that?
Yeah.
So you have your denominators which show peaks.
Yes.
Why would a Cooper pair going from one to another give you a density of states like that, give you a range function like that? Do you have a physical feel for that?
Well, so this is so at this point, this is presumably just the peak in the density of states effect.
Why would that? I don't have a feel for why that would happen for the Cooper pairs transferring from one to another. I don't see why that would give you any change like that. I just
Well,
don't
because
feel
this
for
is
it.
a microscopically occupied state, right? This is a most condensed state, so I have a huge number of Cooper pairs in that state.
So why wouldn't that be at zero energy?
Oh, because basically this is the bias voltage between them, because the chemical potentials are different, right? The Cooper pairs are at chemical potential in each of the leads, and there is a difference in chemical potential, so that's exactly where
I think I'm not used to thinking of the density of states and thinking that as more of a, okay, never mind. Go ahead, Conrad.
So I had another question, since you have this slide, this is good. So I didn't get a sense of, so you have this Cooper pairs which are migrating,
Yes.
so that's fine, and you like that, that gives you a 2 photon, that photon peak. What about the other one where you break them up? Is that actually counterproductive in the sense of output, or is it?
Well, at this point, what comes to this order, again, the high order might be, but at this point, I just break them and they both migrate, so they don't lose the phase information as they do that.
So they recombine then again and give you a photon?
Well, right, so because I have 2 of them, because I have to break a pair, I have 2 of them to generate 2 photons, and they go without keeping the phase information. At this point, I haven't told you anything about what they recombine or not here, because that will be the next order process where I'll see whether it contributes back to this peak. So to second order, I just need to say that they separated and jumped. Right, that's all that I can do. To higher order.
Maintaining the phase.
Yeah.
Okay, do we have any more questions?
I have one more question.
Okay, Conrad.
Is there any physical significance to the, I can attribute to the density correlation?
Well, I mean, this is, in some sense, this is presumably the easier part, because this is just the number of photons with different things. So one needs to, of course, calculate to measure it at the same time. But presumably, it's actually easier than
So it's measurable.
I assume it's easier to measure. But again, how to measure it exactly, this goes into the part of the quantum optics which I don't know. I assume that that's easier than it is easier.
Well, let's thank Conrad again for sharing thoughts. And also, that was really terrific, and thank you all for being here. And now we are going to retire to the poster session. So we'll see you all outside. Thanks.